Howdy folks. In this video I want to prove one of the key facts about the gradient. So what do we assume? We assume we've got a differentiable function at a point and the gradient is not zero there. So what we can prove is that a tangent line to the level curve at that point where the function is differentiable will always be orthogonal to the gradient, again as long as that gradient isn't the zero vector. So let's look at what we're dealing with here. This would be our function f of x, y, which defines some surface living in R3. And what I've sketched on here are the contour lines. Remember, when we draw the lines on the surface, we call them contour lines. Sometimes we call them contour curves. What I'd like to do then is let's look at the projection of those contour lines down into the domain space. So remember that this is our domain we often write in the xy plane. So if I were to project these level curve lines, these blue lines down into the domain space, maybe they'd look something like that. That's a little bit too small there. And maybe have there, and then maybe we have there. So these are the level curves. Remember, these are the contour curves, these are the level curves. So let's take some point in the domain space. We'll label it as A comma B. So that would give us some point up here in our 3D space. This would be the order triplet AB, f of AB, point living on the surface. So what do we have here? Well, the gradient always points in the direction of steepest ascent, which is probably about this direction here. That's going to change your z values the most rapidly. Notice that if we were at some other point, maybe this point right here, the gradient vector would be pointing in this direction. But for where we are, the gradient is pointing in the direction of steepest ascent, meaning if we move our domain values along this vector in R2, the z values as we move along that corresponding curve that we'd get on the function, if we were to put a little curve up here, those z values would be increasing the most rapidly. So let's put a tangent line on this particular level curve passing through the point AB. So there's that tangent line. And so our claim is that this green tangent line that's tangent to this blue level curve here is always orthogonal, always perpendicular to this gradient vector. So again, this vector is the gradient of f at the point AB. So again, here we've got our claim that this tangent line is always orthogonal to that gradient vector, provided the gradient vector isn't the zero vector. So the way we're going to do the proof is going to require us to work with the parameterization. So let's say that this r of t right here gives us a parameterization of the contour line or the contour curve. So r of t is a vector value function of three coordinate functions, right? Some x of t, some y of t, which we'll discuss how to find in a later situation. And then we simply take the x coordinate and the y coordinate, we plug them into the function, and that gives us the z coordinate. So this would describe the contour line that lives in 3 space. So for this contour line that we've parameterized this way, if we project it down into the domain space here, the xy plane, then the third coordinate's always 0, and we can just drop it off. We don't need that. And so the projection of this level curve into the xy space would just be the curve x of t, y of t, where that is going to be a parameterization of this blue level curve line. So the r of t is what I'm using to denote the parameterization of the contour curve in 3 space, and it has an associated rp of t, which is the parameterization of the level curve in R2. So now I think we're ready to do the proof. Again, we're proving that this tangent line, this green tangent line, which is a tangent line to this blue level curve given under this parameterization, needs to be orthogonal to this gradient vector right here. We want to be orthogonal to that gradient vector. So let's see how we could do that. So here we go with the proof. Let's plug AB into our function. That's going to spit out some z0 value. That's this z equals z0 value that we have for this contour line. Then, as I've already stated, we would use r of t equals this to be a parameterization of the contour line, which would be this contour line right here, where f of xy is equal to z naught. So this is the collection of all of the points on this surface whose z coordinate is z naught. That could be described, that this parameterization would give us that. Likewise, if we want to talk about the projection, so I use the subscript p there, this r sub p equals x of t, y sub t, that would describe this particular level curve in the domain space, and this is for z equals c naught there. So notice that because the z naught value is supposed to be constant, we have that f of x of t, y sub t needs to equal z naught. So I've got this statement here, that f of x of t, comma y sub t needs to equal z naught. Then a clever move is to go ahead and differentiate both sides. The reason why we do that is we know how to compute this derivative, and we know that the derivative on the right-hand side will have to be 0, and let's see what happens. So I've taken d dt of both sides, because it's been parameterized, this particular coordinate in this function here is just a function of t as the only independent variable. So I'm taking d dt of both sides. On the right-hand side, as I said, we're going to have to get 0, or we'll certainly get 0. On the left-hand side, though, we'll have to use the chain rule. So here's the chain rule for this function. F is a function of x and y, and each of those are parameterized by t. And so then we can develop the chain rule from that tree diagram. And so here I've differentiated, missing the partial f. So I've differentiated this function right here, following this chain rule. So we do partial f partial x dx dt, partial f partial x dx dt, and likewise we'd have partial f partial y dy dt, and then on the right hand side differentiating a constant gives us 0. So here's the key trick, folks. What we recognize is we've got a sum of these multiplication statements, the sum of these factors being multiplied together, and the key trick is to recognize that as the result of having done a dot product. So we recognize this as a dot product, and so let's go ahead and undo that dot product. And so here you can see I have sort of unfolded this dot product here, and you could just check. If you were to do this dot product, notice that you would get the result of this particular chain rule, that we'd have partial f partial x multiplied to dx dt plus partial f partial y multiplied to dy dt, which is what we had up here. Folks, it's actually this trick is one of the reasons why I really want to do this proof. Besides the chain rule application and whatnot, I think it's really important to see how that trick works. You'll be seeing it again in the course. So as soon as we make that observation, folks, we're almost done, because we recognize that this is the gradient, and this is simply the derivative of our rp of t. That is, if you were to take the derivative of rp of t, you'd get the vector x prime of t comma y prime of t, which is what we stated here. So I wrote this as y prime of t. Well, what have we just done? We've just shown that the gradient is, when we dot it with a tangent vector to the curve rp of t, that dot product is always 0. What does that mean? That means that this vector is always orthogonal to this one, even when we evaluate it at particular points. So then we can conclude, folks, that the gradient is always orthogonal to the tangent lines of rp of t, meaning this green line here is always orthogonal to the gradient at that point. If I were to move to another point on this, maybe give myself a different tangent line over here on a different level curve, the gradient would still be pointing in the path of steepest descent for that particular point. No matter where I put one of those points, the gradient is always pointing in that direction of steepest descent, but then it's always perpendicular to the level curve lines. Folks, I hope this proof was helpful. I think it's a very insightful proof and helps to clarify, one, how all of these components are related to each other, contour lines, level curve lines, gradients, tangent vectors in the domain, but then also what that looks like on the surface itself. So I think it's important to connect those together. But I think the proof has some really useful insights for how we can use the chain rule, how we can sort of undo a dot product to help us out. These techniques are techniques you're going to see again and again in this course. Thanks for your patience. I hope this video was helpful.